Ben ritrovati. È ospite del CED ad oggi il dottor Elvio CARLINO, primo ricercatore dell'Istituto per la Microelettronica e Microsistemi del CNR di Lecce. La sua attività di ricerca dal 1985 è stata dedicata alle applicazioni e agli sviluppi di nuove metodologie TEM-STEM per studi sulle proprietà strutturali, chimiche, elettroniche e magnetiche della materia. Dal 1997 al 2001 ha diretto la divisione di ricerca sulle microstrutture del pastis CNRSM. Dal 2001 al 2007 è stato direttore del Centro di Microscopia Elettronica del Laboratorio Nazionale TASC-INFM e dal 2007 al 2017 ha diretto il Centro di Microscopia Elettronica dell'Istituto IOM-CNR di Trieste. È autore di oltre 150 lavori scientifici su riviste internazionali e oltre 50 relazioni su invito a congressi nazionali e internazionali. Ha organizzato numerosi congressi in Italia e all'estero ed è stato responsabile di numerosi progetti di ricerca. È membro del Comitato Scientifico per l'accesso internazionale alle infrastrutture ERIC-CERIC e ESTIM-3 finanziati dalla Comunità Europea. Giocherà un ruolo importante e fondamentale nella costituenda infrastruttura di ricerca di microscopia elettronica che il Dipartimento di Matematica e Fisica ha proposto nell'ambito della infrastruttura europea CERIC-ERIC. Delle nuove metodologie in microscopia elettronica con risoluzione atomica, capaci di superare i limiti intrinseci della fisica dell'interazione elettrone-materia e dell'ottica elettronica, dei metodi di imaging nella microscopia TEM e STEM, delle informazioni che possono essere ottenute da volumi nanometrici di materia e delle numerose applicazioni della microscopia elettronica in trasmissione a risoluzione atomica, ci parlerà nel suo seminario dal titolo Atomic Resolution Transmission Electron Microscopy, How Imaging by Electrons Can Mimic the Daily Experience of a Human Vision. Dottor Carlino, prego.
Okay, as first I wish to thank Lucio for inviting me here and you for being here today. I'm very pleased to, I spent a long time ago here, and I'm very pleased to share some ideas we developed in the last years in electron microscopy with you. Today I wish to speak about how we can see what it does mean indeed when we see atoms in a matter. The idea to see atoms in a matter is quite old. It starts from Democritus when he conceived the atomistic structure of the matter. And this produced also in people the knowledge and the capability to understand how powerful can be the capability to see the bricks that constitute the matter. This also produced books in science fiction. Here we see one of them. And it was translated in Italian as The Man Who Saw the Atoms. This means that the person capable to see the atoms, he was absolutely not a good physicist. He was, I don't know, he was an hard worker, I think. And, but he was able to produce wonderful equipment only because he was able to see the constituents of the matter, which means that he was able to see something as small as 10 to the minus 10 meter, which is the order of magnitude of an atom in a matter. On the more scientific side, this is a statement of Richard Feynman about the microscopic dream. And of course, it would be really easy to make an analysis of any complicated chemical structure. All one would have to do would be to look at and see where the atoms are in the matter. The problems, as he said, is that at that time, it was a problem also from the point of view of technology. And he said, I put this as a challenge. Is there no way to make electron microscope more powerful? The idea today is also to see if this statement of Feynman is still valid or not. What we need to see the matter as a microscope. not a microscope like this one, simply because this works with the microscope of Galileo, and it was done many centuries ago. Because if we want to see by using light the atoms, we have a limit which is related to what is said by Abbe in the relationship where we see the resolution related to the wavelength we use to illuminate the matter. And he said, there's a wonderful, I think, this statement. He said, according to everything that lies within the field of view of present-day science, a limit is set to the range of operation of our organs of sight by the nature of the light itself. And this cannot be overstepped by the harmony of our... Does it work well? Doesn't work. It's on. Works? Okay, that's perfect. The point is that he said, perhaps in the future, the human spirit might succeed in making use of processes and forces which will allow these seemingly unsurmountable barriers to be overcome in utterly different ways. These utterly different ways, indeed, is electron microscopy. Because if we need a wavelength of 10 to minus 10 meters by using, for example, 200 kilovolt electrons, we have a wavelength of 2.5 picometers. So from the point of view of a wavelength, no problem. The problem is that not enough the equipment. We have to develop methods and knowledge in science and physics to be able to develop methods capable to achieve our goal. In particular, along the years, the microscope was invented in the 30s of last century. At the beginning, it was believed that it was or impossible to develop an electron microscope or completely useless. Indeed, the electron microscopy demonstrated along the year that it was able to overcome intrinsic limits that were postulated at the beginning, and was able to achieve quite good atomic resolution, and we will see in a while. In particular, among all the methods developed in electron microscopy, two of them, high resolution emission electron microscopy and high angle and dark field imaging, have the better performances in terms of resolution. But we will see that if we want to achieve a way of seeing atoms that mimic the way in which in the daylight we see the nature around us, we need maybe something more. One of the limits at the time of Feynman was that indeed the lenses for electron microscopy were too poor. In particular, spherical aberration limited the resolution well above the value stated by the wavelength of the electrons. The problem to overcome this limit were developed a series of methods, and we will see some of them. In particular, one of Dennis Gabor about holography, and Dennis Gabor received the Nobel Prize in 1971 for this invention. How we can overcome the limit of the equipment? From the technological point of view, since the beginning of this century, we can use the aberration corrector for spherical aberration and then also for chromatic aberration that made the resolution of today's equipment of the order of few picometers, 63 picometers. In particular, here we can distinguish the atoms of gallium and nitrogen in the Wurtzite structure seen in projection 211. because we have to keep in mind that when we look at atoms, what we see indeed is something that is related to the position of the atoms, which is because we are able to see where the potential within the matter is located. But there is, nowadays we have a resolution of about 25, 30 lambda with a modern microscope. The problem is that we have another problem, an intrinsic limit, which is the radiation damage. We can image such an image like such a material like gallium nitride, but we have no way to apply the same dose to soft matter or biological sample, because in that case we completely destroy the specimen itself. So another limit today is not so much related to the technological capability of the equipment, but is mostly related to radiation damage, which means that we have to develop new methods to overcome this limit. Of course, when we look at the in transmission and microscope, we even if sight is a tremendous and powerful sense, human sense, but of course we can have some Tromdale, like in this case when we see this strange animal, or like for example in this case where this is a recent paper, and here there are some dislocation, the control of magnetic dislocation in the matter, and the contrast we see here is very similar to this one, or this one, or maybe this one, that belong to this one. So the problem also to be at very high resolution, we have to take care of what we are doing. And the way to, the rule of thumb, the way to overcome this problem, I learned the way to do that about 30 years ago in a school made a few kilometers away from here. And it's due to Severin Hamelings. You can believe what you see as long as you understand what you see and how you see. Now let me briefly and quite quickly speak about standard approach to atomic resolution imaging, let's say standard. In case of high resolution TM, what we see indeed is an interference pattern. And it depends on the experimental condition and on the sample. And this interference pattern produces maximum and minima that can or cannot coincide with atomic position seen in projection in the structure. And also changing the thickness of the specimen or the experimental condition, which means the focus of our objective lens, the position of the maximum and the minima can change. This means that if we want to really say that we have the position of an atom there, we have to compare the structure with a model and with a simulation. This is usually done, this is an image of some years ago. This is gallium arsenide substrate and zinc selenide epilayer, and here is formed a defect. But we can say something about the atomic structure of this defect if we have a model and a simulation to compare to the experimental image. Other example here in the case of titanium dioxide. Here is the simulation by considering the structure of TO2 anatase, and here is a small particle of anatase. Another example here on a more complicated structure, here we have a tetrapods of cadmium telluride seen in different projection. Here the interest was to understand the core of this tetrapod, which can be used for a nanotransistor, and in order to understand how the wave function of the electron can propagate within the structure, we have to understand the relationship between the core and the arms of the tetrapods. And this is done by producing a model, then a simulation, then to compare the contrast with the experimental image. In this way, we can say how this structure can grow in different configuration with one branch, two branch, several branch, and so on. We can understand how the matter works. Briefly to summarize this first step. So seeing atoms and by high resolution TM means to see where maxima and minima are in the structure, which are located to the maximum and minimum potential projected in the specimen. It's an interference pattern. We cannot say so much about which atoms are giving that maximum. We cannot distinguish easily between atoms and atoms. In the case of high angle dark field imaging, we have a completely different way of forming the image. In the first case is clearly a coherent image. In this case, it's completely incoherent image, and the intensity in our result is the convolution of the object function, which means the distribution, for example, of potential in our matter, and the resolution function, which is practically the probe. In the case of high angle dark field, we do not form the image in parallel, but we move a probe, very small, 1 angstrom, on the specimen, and we collect the signal with, at the end, the result that this one, this is, for example, is gallium arsenide seen in 1,1 zone axis, and we see here there is another advantage here. We have that the intensity is in some way proportional to the atomic number of the atomic column we have seen, and this means that we can distinguish between gallium column and arsenic column. So, again, we see the position of maxima of potential, and we can distinguish different Z in projection. Of course, also in the case of high angle dark field imaging, we have to take care about the probe that can produce. Here we are trying to image a dumbbell in silicon in 1,1 projection, and we see that changing the focus of the lens, of the converging angle, we have a different shape of the illumination and different behavior of our image. So we have some extra maxima here that does not mean any. But in this way, we have the way to, in any case, even if changing focus and thickness in a relatively big range of variation, we still see that maxima are still there, even if with different intensity. And if we, once again, have a model of our structure, we can compare tiny and subtle features of the image with, and understand the origin in the matter. This is one cadmium telluride also sticks, and here you see the contrast of the image, of the experimental image, and this is the relevant simulation. By comparison, we can understand how the molecules in the cadmium telluride are arranged. Also, by comparison with the simulation, we can have also information about 3D. So where we see an atomic column in projection on a plane, but if we make a simulation, we can understand where, this is not true for all the atoms, but at least in this case it works, where the atom of cerium is located within the atomic column, by comparison the contrast with the relevant simulation. The point is, also spectroscopy is a powerful tool, but in this case we have, in order to have enough signal-to-noise ratio, we need to expose the matter to high rate of electrons and high dose of electrons, and this means that we are heavily limited by beam damage. So no way to apply this kind of approach to, for example, soul matter or biologic sample. Well, at this point we in order to achieve our goal of seeing where atoms are and to understand who the atoms are in the structure, we need the methods first able to reduce the beam damage, but also we have to try to find a way to maximize the information that we can extract from our experiment. Very often the point is that also we have further information about the structure, but we cannot, for example, when you perform a high-resolution TM experiment, you every time discover that the matter is made by atoms. But we know already that it's made by atoms. Can we use this information a priori to improve our capability of image of a structure, to have more insight on the structure? And the other thing, so what we want to achieve is an image where we can see where the different species are, and this image has to give a realistic description of the specimen structure. And we have seen in the case of high-resolution TM, for example, it's not so straightforward to go from the maximum and minima in your image to the structure of the sample. This is our goal. Let me move first from the point of view of the damage. We have been working for a while on radiation damage materials, starting from some studies on nano drugs. This is a typical diffraction pattern that you see for a fraction of seconds on your specimen, and after a while, this is what happens. So the interaction from between electrons and matter destroys your sample very quickly. Typically, for a biological material, we have a limit at the liquid nitrogen of 5 electrons for angstrom square, and at liquid helium of 20 electrons for angstrom square. So a very tiny amount of electrons. This means, for example, that if we focus with the standard Schottky FEG GaN in an angstrom probe, we have about 10 to 8. So we have order of magnitude higher. We immediately destroy the structure. The idea is, okay, that's very, very easy. We can simply defocus as much as we can and spread the illumination on a much wider area until to achieve a value which is not, that does not destroy our specimen. This is a quite old experiment made by Richard Henderson a while ago, and we see here a low dose image of a biological specimen. You cannot see any. And this is an high dose where you can also only distinguish some particles of gold that were used in the past to help the focus in the microscope. This means that if we use very low amount of electrons, we have no way to see where the particles are, and we have no way to image it. The solution, indeed, is possible. First of all, we have to find a way to locate, a method to locate your specimen where the particles are, and to adjust the experimental condition before to acquire the image. And the answer that we have found recently is by using inline holography. Inline holography is something that was developed, we have seen also at the beginning, was developed by Dennis Gabor to overcome the limitation of the length of the electron, but can also be used for our purposes, because with a very defocalized beam, we can have an hologram which gives a high contrast information about our specimen. This is a typical survey by inline holography made on co-crystal of caffeine and glutaric acid. In this case, we used 0.2 angstrom per square for electron for square angstrom And these are the particles. We cannot say so much about what is inside there, but we can see the particle very easily. But also, as we are dealing with holography, we have information, and we acquire this information in the reciprocal space. We have information about the particle shape, roughly, but also about the diffraction pattern. So we also have information how the particle is oriented with respect to the beam, which is extremely important to understand if we can perform an high-resolution TM experiment or other. No? Or, for example, if our specimen is made by particles amorphous, and so on. In this case, the experiment has been done at room temperature by using standard detector or CCD camera. And this is I've been posted in, this is the hologram. And this one can be also used to tune the electron optical condition in order to acquire properly an image in the direct space, which is this one, for example. This is caffeine and anthranilic acid, this one. You see the small particle here and the position of the atoms in the structure and the relevant diffraction pattern. Here is caffeine and glutaric acid. So indeed we can have, by using this approach, we can have the way to locate where the particles are, understand how the particles are oriented, adjust the experimental condition, and acquire the image. This is another example of, in case of impositing, and here we can see also the defect here. This indeed is a way to look at really single particle. Usually the approach, also like the standard cryo-TM, used to reconstruct one single particle by using an average of several particles that are supposed identical. So we have no information about eventual defects inside one single particle. And we learn from material science that in many cases the properties of the particles is not done by the shape only or the structure, by the defect inside. With this approach we can indeed study real single structure. This is another example of phenkamine. This is another example of a little bit exotic about this approach to see biologic material. This is a study of fiber of linen. Indeed, the fiber of linen was obtained by the Turin Shroud, and here is the fibers are covered by extremely tiny particles. Here, this is the image we obtained first. Is a kind of all the line of the Turin Shroud is covered by this particle with some black dots inside. We cannot understand at the beginning what it was. This is the spectrum. We cannot say any because also we have a grow up immediately of contamination, and so we can just say that there are some of these elements inside, but we cannot say that they come from here, here, or here. And the way to understand was by imaging in low dose way. This is, for example, the particle dart we have seen before, and by simulation and comparison of simulation with the structure. Indeed, they are made of ferrihydrite, which is the small particle contained in the hemoglobin in the human blood. And this, away from the dark particle here, is the structure of creatinine. At the end, the structure is creatinine bound to ferrihydrite. So we can really look at biological materials. Well, so we have a method for low dose, for survey, and also for imaging, at least partially. But at the same time, we need to develop some methods to maximize the information we can obtain, or to put information we already have inside our experiment in order to have more images, resembling more closely something that can be interpreted in also a direct way. So what we have to do is to develop methods capable to maximize the information contained in atomic resolution image, with higher accuracy, of course, recovering eventual data that we have lost in the experiment. In the last year, we have been working on coherent diffraction imaging, and we believe that this is an approach which in the future can be, but also even now, can be applied in whenever we want to have accurate atomic resolution information on our specimen. I show you some information how, for example, we can recover the phase that is lost in the diffraction experiment, as we know, is the famous phase problem of crystallography, and also partially at least recover data that are affected by dynamic scattering effect. I will not go so much in the detail in this, but of course you can ask if you wish. Just as a small introduction, if we are able to illuminate a specimen, collect the diffuse wave, we can apply the inverse Fourier transform, for example, and reconstruct the object function of our specimen, at least in principle. Because in practice, there is also another advantage from this point of view. The image we reconstruct is related to the highest frequency we can measure in our diffraction pattern. It's not related. We, in some way, overcome the limitation of the lens. The only problem is that, as known, what we measure in the reciprocal space is the intensity, and not the phase and amplitude, and then the phase is completely lost. And the phase is not something with small information, but most of the information contained in an image is contained in the phase. This is an example, and quite funny. There are two Nobel Prizes for direct methods. There is Carle and Hauptmann. And this is Carle with his amplitude and phase. Hauptmann with his phase and amplitude. And this is by using the Carle amplitude and Hauptmann phases. And you see that it resembles this one. So most of the information is contained in the phase that we lose in our experiment. So can we recover the phase? The answer is yes, related to the Shannon Theorem, which say that any function, fx, y, non-zero in interval a, can be fully reconstructed by simply its Fourier transform at the Nyquist frequency. This was developed for completely different stuff a long while ago to reconstruct the image from the radar equipment. A few years after this publication, David Sayer said that, okay, this is the way we can use to reconstruct the phase, starting from the information only we have. This is the fast Fourier transform in practice of this one. We have completely lost the phase. So in practice, we have an equation where we have a number of unknowns, which is at least double the number of equations we have. And the way to overcome this ill-posed problem was proposed by Sayer in theory in 1952 and was demonstrated about 50 years after. 50 years after in a paper published on Nature. And the reason why we have 50 years from here to here is related to the quality of the information was possible to have in the year when Sayer made his hypothesis and 50 years after, which means that in any experiments we lose not only the phase but many other information, because we have problem with detector, with the drift of the specimen and so on. And the quality of the data is fundamental to recover eventual intrinsic problems we have had with the phase. After a few years also, the same was demonstrated by using electrons in ATM. The way in which the phase is retrieved is by using a recursive approach, which at the beginning was introduced by Gerber and Saxton, and then developed after by FinUp. We start from the information experimental information, the intensity in the reciprocal space. Then we have some constraints, which are what we have measured really. Then we do an inverse Fourier transform and go in the direct space here, where we need a priori information to overcome, to produce the equation we have lost losing the phase, which means some information a priori that can be collected by using, I don't know, another way to have the shape, the size of our particle, and this is the constraint in the direct space. Then, by the Fourier transform, we can go in the reciprocal space, apply the measured intensities, and by a kind of recursive approach, we can reconstruct the image. This is what is done by using X-rays, but it's even easier by using electron in ATM, because in ATM you can acquire your diffraction data. And the information about the shape, you have a rough information, relatively rough information about the structure of your sample by looking at the image. All the experiments I show you were obtained by using standard TM microscope, not CS corrected, with a resolution that shares the focus of 1.9 angstrom. This is just an example, a particle of TO2. Here you see the reciprocal space looks very, we are confident that this is an attest TO2, but we have a problem because this intensity is forbidden for this structure. By doing electron diffractive imaging experiment, we can understand why we have that extra spots. In particular, this is the experimental results we obtained. It is the diffraction pattern here, and we see that the smallest amplitude we can measure here correspond to a spacing of 70 picometer. This is the reconstructed image, and here in the reconstructed image we see the structure of TO2 with titanium atoms, oxygen atoms, and the other columns here. The resolution by simulation, the resolution is 70 picometer according to what we have measured as higher frequency in the reciprocal space. The point is that by using this kind of approach, where we were limited to a resolution of 1.9 angstrom by our equipment, we achieved a resolution of 70 angstrom. That was, the details are published here, was possible to detect small deformation within the structure of TO2, and this is related mainly to the presence of vacancy within the structure of TO2, which are related to the photocatalytic properties of that material. So at the end, quite important information. After some years, how many? 5 minutes? Perfect. We made a kind of generalization of the approach. At the beginning, it was for a single particle. We demonstrated that by self-confining the illumination, we can also study areas of extended particle. This is an example applied to silicon in 112 zone axis. This is the high resolution image limited by the aberration of the microscope, and here is the coherent diffraction, coherent diffraction we obtained, and here we see the frequency at 73 picometer, and the next step is to use such a resolution to distinguish. This is the reconstructed image, and we distinguish the dumbbell of silicon seen in 112 projection with a resolution of 78 picometer. The next step, details you can find here. Next step is to use the approach of data reduction to not only to handle our data, but to remove eventual spurious intensities in the image in order to be able to measure more accurately the genuine intensity within. And then also, I show you very quickly the improvement we have done in this work also from the point of view of phase retrieval algorithms. There are, as in any experiment, it is quite complicated experiment also because the microscope was not designed for that kind of experiment. There are no, at the present, microscope designed for such a kind of experiment. It was a kind of, we use the flexibility of our equipment. This is typical spurious intensity that you can have in this kind of experiment. Here you see that some intensity spurious are of the same order of magnitude of genuine reflection that we want to measure. For each kind of problem, we developed algorithm to remove the spurious intensity and to improve the specimen. Something like that. The next step now is to use eventual a priori information we have about the specimen to improve and to extract, to maximize the information that we can extract from the experiment. This is strontium titanium trioxide. This is the relevant diffraction pattern. You can see here that in this experimental condition we distinguish maxima that are 3.9 nanometer, 0.39 nanometer. This is the structure of STO, and here is the simulation. And you see that in practice we are seeing this one and this one. In fact, in this experimental condition, in the standard high resolution TM, we have no maxima for this atomic column of oxygen. In a TM experiment, the point is that the intensity are also smeared by dynamical diffraction. And it is a big problem that indeed in the years produced several problems in the application of standard crystallographic approaches that were developed for X-ray to diffraction with electrons. But the effect of dynamical interaction can be at least partially overcome by using eventual information that we achieve during our experiment. For example, we can have at least a rough information about the chemistry. So, and if we consider the theoretical zero-order structure factor, we can in some way limit the details are reported here, but in any case we can limit the effect of dynamical diffraction, achieving a result where the dynamical range is improved. But what is more important is that we partially recover the intensity by the effect of dynamical interaction. We will see the results in a while, also together with the phase retrieval algorithms. What we have done quite recently, as a couple of years ago, we developed some mimetic algorithm to phase retrieval. And they were obtained by hybridizing a genetic algorithm which guarantee a better and more efficient exploration of the space of the configuration, even by using optimization algorithms like input, output, or error reduction, which are standard phase retrieval algorithms. The details are here. This is an example where we apply standard. This is the solution. This is the reconstruction by standard approach. This is the reconstruction by our methods. With standard approach, we have an error of about 10%. In the reconstruction, we have an error of 1.5%. Also, from the point of view of the knowledge of the support, we demonstrated for the first time that we can start from so-called random phases. This is the experiment we have performed on STO, we have seen before, and this is the reconstruction. And we have all the maxima coinciding with titanium dioxide, and also oxide columns. Here you can see the comparison between simulation and reconstructed image. And also we have information which is directly related to the atomic number of the species, which means that we know where the atoms are and who the atoms are. This is another application to an interface of STO, lanthanum, strontium, magnesium oxide, which has a tremendous importance from the point of view also of technological application. And here is the interface that we are quantifying by using our approach. This is another example in case of gallium arsenide zinc selenide. And here, all the routines we have developed so far are part of a user program with the user interface that help to understand and to process such a kind of experiment. We are really at the end. This is the summary. What we believe is indeed that from some point of view, we can say that we now are able to see the atoms in the matter, and we have seen how, and also to understand the different species in the structure. I believe that the combination of low dose approach with coherent diffraction imaging in the future will help also to get such a kind of results in biologic sample and soft matter. Thanks to the collaborators, and thank you to everybody for your attention.